Next question is, determine the main dimensions and winding details of a 125 kVA 2000 bar 440 volt single phase shell type transformer with the following data. Voltage per turn is given, maximum flux density is given, current density, window space factor is also given. The hint is given as HW by WW is equal to 3, and also core depth to width of center limb is given as 2.5. So this problem is to find the main dimensions of single phase shell type transformer. So moving on to the solution. For single type shell type transformer, the width of the window is W is equal to WW plus 4A, and the center limb is equal to 2A, and height of the transformer is HW plus 2HY, that is equal to HW plus 2A. So using these two equations we can find the width of the transformer as well as the height of the transformer, and dy is the depth of the yoke is equal to B. So here core depth to width of center limb is given as 2.5, that is core depth is B by width of the center limb is 2A, that is equal to 2.5. Okay, so here core depth to width of the center limb is given as 2.5. Core depth is denoted by small b, and width of the center limb is 2s, that is b by 2a is equal to 2.5. Et is equal to 4.445 mF. So in the question it is given as 11, and we know the value of frequency, and also we know the value of flux density, maximum flux density. Therefore, AI is given as 0.03963 meters square. And also we know that AI is equal to stacking factor into AGI. We need to know this equation. AI is equal to stacking factor into AGI. Therefore, AGI is equal to AI by stacking factor. Okay. So we got the value of AGI. And also in the question, it is given as B by 2A is equal to 2.5. Okay, so we have gross cross areas AGI is equal to what? B into 2A. B into 2A is AGI. Okay, so from this equation we will get B as 2.5 into 2A. So B is given, B is 2.5 into 2A, that into 2A, that is equal to this AGI value, that is 0.044. So we will get the final value of A as 0.0663 meter. Then the width of the limb is 2A, therefore we will get the width of the limb by substituting the value of A, and the depth of the yoke is dy is equal to B, that is B is equal to what? 2.5 into 2A. So we got the value of depth of the yoke also. Then the height of the yoke for a shelf type transformer is HY is equal to A, and the width of the side limb is also is A. Okay, now we need to find the overall height and overall width of the shell type transformer. So output equation of a shell type transformer is Q is equal to 2.22 BMF AIAW delta and 10 raised to minus 3 into KW. So we need to by heart that equation. So in the equation Q is given, BM, F, AI, delta, KW, everything is given. So from this equation we will get the value of AW. We knew that AW is equal to HW into WW. And we will substitute the value of AW, and also we know the HW by WW is equal to 3. In the front of the question it is given as HW by WW is equal to 3. So we substitute that here. Now we get the value of WW, and HW is equal to 3WW. Okay, so according to the equation W is equal to 2WW plus 4A. So we got the width of the transformer. Now the height of the transformer is equal to HW plus 2 HY. So substituting that, we got the height of the transformer also. So in the question, additionally, we need to find the winding details. So to find the winding details of the transformer, we need to first find the primary windings. Okay, transformer has two windings, primary winding as well as the secondary windings. So if in the question of winding details is asked, we need to find both the primary windings as well as the secondary windings. Okay. So this is a single phase transformer. Therefore, the primary winding we can find as P is equal to V into I. In the question, P is given as 125. The question it is given as, see, 125 kVA. Therefore, P is equal to 125 into 10 cube. Okay, is equal to primary side voltage, that is 2000 into I. From this equation, we will find the value of primary side current I. Now we know the current density formula as current density is current by area. So current density is given in the question, and current we got from here, and from here we will get the area of the primary winding. Okay, so we found the primary winding current as well as the area of the primary winding. Now we will go to the secondary winding side. That is for the single phase transformer, P is equal to V into I. So V is the secondary side voltage. From here we will get the secondary side current, and current density is equal to current by area. This current is the secondary winding current. Okay, so here we will get the area of the secondary winding. Next, we will be going to find the number of turns. Okay, so normally number of turns is equal to total voltage by voltage per turn. So in the case of primary winding, number of turn N1 is equal to total voltage, that is the primary side voltage divided by voltage per turn, that is given in the question as 11. So we got as 181.81. Since it is decimal, okay, 181.8. So after decimal it is 8, so we added 1 point here, that is 182. Okay, so turns should not be in decimal, that's why we approximate the value to 182. And also the secondary turns winding, N2 is equal to secondary side voltage by number of turns, that is equal to 40. So additionally we found the primary winding details also. So in the question, if the primary winding details is asked, we need to find the current, then area of the primary side as well as the secondary winding, and also we need to find the number of turns and secondary. For three phase winding, this equation it will be changed. Okay.